And we ask, what's the interaction defined at that boundary? And again, physics and particularly quantum theory provides a very simple way to characterize this universe that we're talking about, called a Hilbert space. We can think of that Hilbert space as composed of a very large number of binary degrees of freedom, answers to yes-no questions. John Archibald Wheeler famously talked about the universe as being characterized by yes-no questions by observers such as us or any other observer. So we can think of this universe as just a whole bunch of binary degrees of freedom that can have two values. That forms a very simple Hilbert space, a space of qubits, quantum bits. And these binary degrees of freedom don't have to be up or down. Each one could be in any combination of up and down. That's what quantum theory gives us instead of classical theory. And so we have a really simple system to think about. So if we draw a boundary across this universe that separates some system that we're interested in and everything else, which we can call its environment, we can ask how the system interacts with its environment. And when we ask that question, we're faced with three basic choices. And the choices are about how big the boundary is compared to the system. So if we think of the system as a bunch of degrees of freedom, and we can ask, in a sense, how close are those degrees of freedom to the boundary? So how involved are those degrees of freedom in the interaction that's going on at the boundary? I mean, you can imagine a system in which the system is pretty small, but its boundary is really enormous. And so all of its degrees of freedom are tightly clustered up against the boundary, so they're highly involved in its interaction with its environment. And you can also imagine a system that's really big, but a boundary that's really small. So the system just barely interacts with its environment. So, you can think of a system that has zillions of degrees of freedom, but its boundary is a tiny, tiny communication pathway that allows it to send a bit back and forth with its environment. So there's almost no interaction at all. So the system can't know anything about its environment. And neither of those are really the case we're interested in. We're interested in systems that have what Carl Friston calls internal degrees of freedom that can have values that don't depend directly on the interaction with the environment. And it's those systems that have those internal degrees of freedom that can do interesting computation. If we're thinking about systems that communicate with their environments via some boundary, then we're interested in the ones that exhibit some interesting behavior and can do some interesting computation, and so can get information from their boundaries and actually do something with it. Clearly, biological systems are systems like that.
Right.
You can think heuristically of drawing the boundary of a cell, for example, at the cell membrane, or the boundary of a human at their skin. These boundaries in Hilbert space don't match up with boundaries in geometric space, 3D space. They're actually boundaries in spaces of enormous numbers of dimensions. But just as a kind of thinking tool, we can think of things like the cell membrane as the boundary of a cell. And there's lots and lots of stuff going on in the cell that doesn't directly depend on what's happening on the membrane. It all depends on it eventually, right? What the cell is doing is a lot of processing of information that's arriving across its membrane. And then it's acting on its environment via its membrane. So the membrane's important. It's just not the whole story of what's going on inside the cell. So let me just say one thing about this picture, which I think is important to the free energy principle and thinking about systems in general. And that is that, I'll say two things actually. If you have systems like this that have internal degrees of freedom, so they're not completely, their behavior is not completely determined by what's happening on their boundary, then these systems have a certain kind of freedom, which is the freedom to assign the semantics they want to the information coming across their boundary. And in physics, we call that the freedom to choose a basis for describing the interaction with the boundary. So a basis meaning a set of vectors that describe what's going on in the Hilbert space. And this is a very fundamental kind of freedom. And there's an important theorem in physics that was published 2 decades ago, probably by Conway and Kochen, called the free will theorem. And the first version of their theorem used mostly reasoning from relativity theory to show that if you have two interacting systems and one of the systems has free will, quote, free will, in the sense that its behavior is not completely determined by what's going on in its past light cone, which means everything that's causally antecedent to it, then the other system that's involved in the interaction isn't completely determined by its past light cone either. And then they strengthen the theorem by not making it relative in this way, but pointing out that if observation obeys some fairly obvious characteristics, that systems are not fully determined by what's going on in their past light cone. Well, you can think of the past light cone as crossing a boundary to get to you, crossing your boundary to influence you. So this is the same kind of freedom that we were talking about earlier. It's a freedom from local determinism. And it characterizes any systems that are statistically independent of their boundaries, conditionally statistically independent of their environments, sorry.
Right.
And it's this condition that allows systems to be regarded as computing something interesting. And indeed, it's this condition that allows systems to be regarded as having their own states, having states that are determined by them, not determined by their environments.